So good afternoon, everyone. So I welcome all of you to the day 8 of our online ELICT FDP on cloud and fog computing platform for IoT application. So today we have again two sessions. In the first session, we will discuss about resource allocation and task scheduling algorithm cloud computing. And in the next session, Professor Chandrasekhar from NIT Raipur will discuss about effective fog and edge computing based intelligent healthcare system using machine learning. So this is the agenda for today's 4-hour session. So let us start the first session. So in this session, we'll see two important problems related to cloud computing. The first problem is resource allocation. Second problem is called as task scheduling. You can find numerous research paper in both domain, resource allocation and task scheduling. But people use this term resource allocation and task scheduling alternatively, but they are different. So we'll discuss what is the difference between resource allocation and task scheduling, which technique or which phase follows which other phase. So resource allocation is following task scheduling or task scheduling is following resource allocation, that we'll see. So apart from that, we'll see some of the topics which I have mentioned here. So although we say task, application, job, these terms alternatively, but there are difference between these terms, lease, application, job, and task. They have specific meaning, but if you look into dictionary meaning, more or less they are same. But in the field of resource allocation and task scheduling, these terms are completely different. So first we need to understand what are the difference between these four terms. Then we'll go for the difference between resource allocation and task scheduling. And once you understand the concept of resource allocation and task scheduling, we'll see a couple of algorithms under resource allocation and couple of algorithms in task scheduling. For example, in under resource allocation, I'll tell you a very popular algorithm which is implemented in Hygia Open Resource Manager. Hygia is a open resource manager that you can download. If you have a Linux system, you can download Hygia and perform resource allocation. That we'll discuss. And after that, we'll discuss one of the improvement over the Hygia algorithm that is called as dynamic provisioning scheduling, DPS algorithm, which is performing better in comparison to the Hygia algorithm. And there is another algorithm that is called as alert time based resource allocation, ALTRA. So this algorithm is again an improvement over the Hygia and DPS algorithm. Apart from that, we will see a fairness based resource allocation algorithm. Then we'll discuss about the posted price model, which maps a set of tasks with a set of machines. So posted price model is based upon a very popular algorithm of mathematics, which is called as Hungarian algorithm. So based on the logic of Hungarian algorithm, people have implemented the posted price model. So these are the algorithms that we are going to discuss under the resource allocation. Similarly, under task scheduling, one of the popular scheduling paradigm under cloud is that multi-cloud scheduling. And future of cloud is also multi-cloud. So one cloud is going to associate with another cloud, and like that, all cloud service provider they will combine each other to provide unified service. So we'll see the concept of multi-cloud scheduling. Under multi-cloud scheduling, we'll see two popular algorithms. One is round robin, another is called as list scheduling. So round robin is obviously a very popular algorithm, but it has some drawbacks in the context of multi-cloud scheduling. So there is another algorithm which is an extension of round robin algorithm that is called as list scheduling that we'll discuss. Then we'll see the concept of workflow scheduling. In fact, for computing platform or IoT, or you talk about cloud, people represent it in the form of a data flow graph, or they represent in the form of a directed acyclic graph, or it may be represented as an application. And finally, we assign these tasks into our resources. So that is comes under the workflow scheduling. So these are the algorithms we are going to discuss under task scheduling, followed by the conclusion. Now, coming to the difference between the resource allocation and task scheduling. So these terms are generally used alternatively in many research articles, but the term resource allocation is different from the term task scheduling. For example, you developed an application and you want to deploy that application in cloud. So last lecture also we discussed about the cloud analyst, in which I told developer has to concentrate on the logic part. They should focus on the application logic rather than the deployment, rather than the maintenance and other scalability and other factors. So you have developed a particular applications and you want to deploy it in cloud. You want to deploy it in cloud. So in order to go for this deployment, suppose you need, let's say, 30 machines, or you can say 30 virtual machines are required to host these particular applications based upon the demand of these particular applications. So if a particular cloud service provider, let it be Amazon, or let it be IBM, or let it be Google. So if they provided 30 machines to a particular user to run their application, so that is said to be the resource allocation. So 30 machines are called as the resources. So whether they need a computational resources or they need storage resources, that is provided by your cloud service provider. Once these resources are allotted to you, that we call as a resource allocation. On the other hand, we have task scheduling. Suppose 30 machines are assigned to you. So now you can decide, uh, let's say your application is a service oriented architecture based application, or you can say microservice based application. So in which your application is divided into a small part. So you have decided that let's say the part one is going to execute in this machine, part two is going to assign to this machine, part three is in this machine, let's say P10 is in this machine, some P30 is in another machine, like that. So you are basically making a ordering to dispatch your task, or you can say your module, to these resources. So when ordering comes into picture, that we refer as task scheduling. So resource allocation is to provide whatever resources required by the client. If the provider is willing to provide that one, that is called as resource allocation. But once you get your resources, in which order you are going to process, that basically focus on the resource. Task that focuses on the task scheduling. So task scheduling is basically determining the order of execution of a certain task. So finding a order is very much challenging. Always fast come fast of order, it may not be the good one, right? FCFS is simple, but there are other approaches people have developed in which they have shown that if you process other than the FCFS order, the performance is better. So basically, this is the difference between these two terms, resource allocation and task scheduling. So in some cases, we use resource allocation, some case we are using task scheduling. And together we call that resource allocation and task scheduling. But there is a difference between these two. Similarly, here also you can see we have lease, we have application, we have job, and we have task. So basically, these terms are also having some differences. For example, if you look into an application, right? Application is nothing but a data flow graph. For example, if I take a application like this, so A and B, C, and let's say D, and this one is, let's say, E. So this is an application, okay, where you can see A is called as the start task, or we can say parent task, and is called as exit task, okay, or you can say end task. Both D and E can be considered as a exit task or the end task, right? And you have seen that this is called as a precedence constraint application. Precedence constraint applications means, so there is a dependency between the task. Okay, precedence constraint means you can see B and C, they cannot execute until unless A is executed, right? Similarly, E cannot be executed until unless B and C both are completed, and D can only be complete once B is completed its execution, right? So there is a dependency. You cannot violate this dependency. Even if the resources are becomes available, it is not possible to allot B and C prior to A. So once A is completed, then only you can think about B and C. So that's why it is called as precedence constant application. So each and every application has a arrival time. So if you are dealing with multiple application, so each and every application is given with a arrival time. And each and every application has a mode of assignment. Mode means you can simply say it is a priority. So when multiple applications are assigned to you, then you can decide which application is having more priority, which application is less priority. Okay. So in that context, we are using this word that is called as application. Okay. And a job is a collection of tasks, right? For example, I can say this B, D, E. B is a task, D is another task, E is another task. So B, D, E together, I can call it as a job. Generally, we take a set of tasks under a particular job. For example, I can say job J is equal to task T1, task T2, and task T3. Okay, so a job contains a set of tasks. Okay, and task is the smallest unit of a particular job. Similarly, task can further be divided into subtasks. Okay, if you want to go for minute level, you can say deeper level, you can find a subtask. On the other hand, these terms, these application, job, and task, these are more or less used in the task scheduling term. They are not used in the context of resource allocation. However, the concept of lease is taken in resource allocation. So lease is generally just like a formal agreement. Like, suppose I am talking about constructing a particular building, or if I can take an example like building a bridge. So XYZ construction, let's say, is given this lease to construct a building, or XYZ construction is given the responsibility to build a bridge to connect, let's say, two different villages. Okay, something like that. So in that case, what we have some formal agreement. So every lease has a formal agreement. At what time you are going to start, at what time you have to stop, what are the resources you are going to use. So these all terms are mentioned in the lease. So like unlike this application, job, and task, lease is more formal. So you have to specify some of the parameters, right? Without that, it is not possible. Every lease has a deadline. So you have to complete it before the deadline. Otherwise, the lease is document, whatever mentioned, they are going to be violated. So in this way, you can see these terms are different from each other. And you can see these terms throughout this particular session that I am using these terms while I am discussing different kind of resource allocation and task scheduling algorithms. Now, if you go to the very popular open resource manager for resource allocation, that is called as Hygia. So you can download Hygia. It is open source. It is free. So you can download, but you need Ubuntu system, right? And you can configure. So when you install this Hygia successfully, you will get a set of nodes. So I am showing you a simple example so that you can understand what happens inside the Hygia. So here you can see x-axis represent the time, y-axis represent the node. So when you install Hygia, you will get a set of node. For example, you got, let's say, 4 node cluster. 4 node cluster means you can say this first node, this is my second node, this is my third node, this is my fourth node. These 4 nodes are connected through a interconnection network, right? So it is a 4 node cluster. In your group, there are 4 different types of nodes are there. So as we say cluster means all the configurations, or you can say all the architecture, or the interfaces and everything is common for this 4 node cluster. Okay, having same architecture. All nodes are having same architecture, same type of operating system, and other things. That's why it is called as cluster. So they are, even if you can say, they are identical to each other, right? So here you are given with a 4 node cluster. For easy representation, we consider node 1, node 2, node 3, and node 4. But all the nodes are equally capable. If a task is done by node 1, the same task can be done by node 2, can be done by node 3 and node 4 respectively. So over a period of time, what you have to do, you have to assign, uh, over a period of time, you have to assign the nodes to different lineages. Suppose you have 5 lineages, L1, L2, L3, L4, L5. So each lineage has some requirement, right? Let's say it will start at a particular time, end at a particular time. What is the duration? How much you are going to pay? So lot many things are there, right? So based on the requirement of these lineages and with respect to 4 nodes, you are going to assign it. Okay. So for example, somebody is asking 2 node, you can provide here, right? 2 node you can provide. Somebody is asking 3 nodes, so you can provide only after this particular period of time. So like that, over a period of time, you have to assign a set of lineages to a 4 node cluster. And that is our overall objective in case of resource allocation. So, but these lineages can be submitted in various modes. Modes means various priorities. Like you know that some leads may be having more priority, some leads having less priority. Let's say in construction, if we feel that 4 lane road can be extended to a 8 lane road, right? And construction of a bridge, right? So construction of a bridge has more importance because it is disconnected. Both area is disconnected. So if a bridge can be constructed, then we can connect these two part, right? So in comparison to this 4 lane road extended to 8 lane road, this is having more importance, right? So every lease is having some kind of priority, right? If higher priority lease is there, we will give more importance to that particular lease. If it is a low priority, then we will give less options to that particular lease, right? So there are different type of leases available in our resource allocations. So not only these leases arrival time and other things you are going to check, but also you should think about what is the mode of this particular lease. Now let us understand there are different type of leases. So I am showing you the first type of lease, that is called as AR lease. AR lease stands for advance reservation. So what is advance reservation? Advance reservation means simply I can say like you have booked your train ticket. You know a particular, you know, you are aware of a particular train which starts from one source and reach to a particular destination, and you can say the source to destination, you have booked a particular seat in a particular coach, right? So for instance, you have booked resources from, let's say, 1 p.m. 13 means it is 1 p.m. to, let's say, 2 p.m. Okay. So how many nodes you have booked here? You have booked 3 nodes in advance reservation mode. So in order to book a lease under advance reservation mode, you have to provide either the start time plus duration, or the first option, or you can provide the start time plus end time. So these two things you have to specify. For example, if a lease arrived at 1 p.m. and its duration is 1 hour, so obviously you can infer the end time is 2 p.m. Or if you go for the second case, start time you know, end time you know, where you can infer duration. Okay, so in order to submit a advance reservation list, you must specify the start time and duration. And always arrival time is less than the start time. So if start time is 1 p.m., that indicates that your lease should arrive before that one. Then only it can be possible for any cloud service provider or lease provider to provide the resources, right? And AR lease is the, you can say it is the highest priority lease in the in HYGIA, the Open Resource Manager, or any resource allocation algorithm. AR lease is given as more priority because it has a specific start time and specific duration, or specific start time and specific end time. Right. That is the reason why AR lease is more having more priority. So in this case, AR lease is asking you three different nodes. So you can see it has covered node 1, it has covered node 2, it has covered node 3. So three different nodes are asked by that particular lease. So if you say that AR lease, no, the resources are not available, you can start at 1.5 and you can complete at 2.5. So it is not possible. Okay, AR lease case, you have to specify the time. At no case, the lease can be shifted with 1 minute or 1 second. 1 p.m. means it should be started at 1 p.m. Right? Like we book our ticket, right? From X station to Y station, we book a particular seat in a coach. So that seat is valid whenever you reach to the Y station. Okay, once you reach to Y station, the ticket is no more valid. Right? Another person can may occupy that particular seat. Okay, but this is stringent, right? If you specify specific time, so it is very stringent. So stringent is not good, right? You should be very flexible. So in order to avoid that, so there is another type of lease that is called as the best effort lease. So best effort lease case, we don't have any specific start time, we don't have any specific end time. Rather than we have duration. Okay, you have duration. We don't have any start time. You cannot specify that your lease is going to start at 1 p.m. or 2 p.m. because you are not aware of it. At what time it will complete, that also you don't know, right? So only you have to specify what is the duration. For example, I am specifying my duration is 1 hour, right? So a cloud service provider may give you time from 3 p.m. to 4 p.m. A cloud service provider may give 8 p.m. to 9 p.m. Okay, a cloud service provider may give, let's say, 8:30 p.m. to 9 p.m. and let's say 9:30 p.m. to 10 p.m. So it is two half-an-hour slots to fulfill your request. So best effort lease is just like our platform ticket, right? We go to a particular station and we book a particular ticket, right? Or we have taken a particular ticket to travel from X to Y, but there is no reservation. You can travel in any train in general coaches, right? But which coach you are going to go, you don't know, right? When you are going to reach your destination, that also you don't know because it depends upon the next train arrival into a particular station. So it is simply like a best effort list, right? So any train you can travel, any node you can be assigned at any point of time. That's why it says that as soon as the resource becomes available, that is going to provide it to you. If resource is not available, your request is simply put in a queue. You have to wait until unless the next resources is going to available. If resource is not available for indefinite period of time, then you are not going to get resource up to indefinite period of time. So obviously, best effort lease is having low priority in comparison to the advanced reservation lease. Right? If somebody is giving specific time, definitely the cost is more. When you are not specifying a specific start time, the cost is less, right? So obviously, best effort lease is having less priority in comparison to advanced reservation lease. And priority means what you can say here. If a best effort lease is assigned, assume that a best effort lease is assigned somewhere, right? Then if a advanced reservation lease is arrived in a system and it is demanding the resources which is occupied by the best effort lease, then it is going to be preempted. So best effort has to release the request, and advanced reservation is going to occupy the request. This is also you can compare with practical situations. Like in many trains, you can see there is a D coach. Okay, generally intercity coach, intercity train, we have D coaches. In D coaches, reservation is there. But if reservation is not there for a particular seat, then anybody can sit. So sometimes reservation is done between X and Y station. Okay, let's say one person is traveling from W to Z. Okay, X and X to Y, there is a seat reserved in the D coach. So the person who started his journey with W can occupy the seat up to X station. Okay, just like a best effort leads. But when it reaches to X station, another person is going to come and request him to release the seat, right? So the next person who booked X to Y, he can occupy this one. And again, Y station, his journey is going to complete. So the person who is there in the best effort mode can continue to sit in that particular seat from Y to Z. Okay. So if nobody is there in a particular seat, nobody booked a particular seat, anybody can sit there, right? But if somebody has done the reservation, whenever he reached in that particular position, you have to release your resource. So that is called as your best effort list. Again, this best effort list is available in two mode. One is called as primitive best effort, another is called as non-primitive best effort. So in operating system, we know primitive means in between you can stop, and in later point of time you can resume. For example, you can see here 8:30 the best effort lease has started execution, but 9 p.m. we have preempted it. Okay, after 30 minutes of execution, so we just preempted that particular best effort lease, right? Again, we started at 9:30 p.m. and we continue up to 10 p.m. So this is called as a primitive. But non-primitive means once resource is given to the best effort lease, it is going to release the request only after its completion. In between, even if there is a high priority lease is arrived in the system, you cannot preempt it. So that is called as a non-primitive best effort. So this is also an example of a non-primitive best effort. We started at 8 p.m., completed at 9 p.m. So in between there is no disturbance. But in the case of primitive one, you may have multiple disturbance also. For example, I can say 8:30 to 8:45. You got a 15-minute slot. Let's say 9:15 to 9:30, another slot. Let's say 10:20 to let's say 10:50, another slot. So there may be multiple preemption also. So that type of lease is called as a primitive best effort lease. So whenever resources becomes available, we are going to provide it. If resource is not available, we are not going to provide it. Or high priority lease is coming, we are giving more emphasis to that high priority lease. Only in the case of non-primitive case, once you start a best effort lease, it is not possible to preempt it, right? So that is another type of lease. So you can see this situation. Now you can understand a best effort lease has started its execution, but in between an AR lease arrived to the system. Okay, so what happened? The best effort lease is preempted, and once the AR lease has completed its execution, again you can resume the best effort lease. Okay, so it is an example of a primitive best effort or non-primitive best effort. Obviously, it is an example of primitive best effort, right? Because once its execution is started, okay, in between you have preempted. Okay, but for example, if AR reach I am going to cancel, so that is can be considered as a non-primitive best effort, right? But normally best efforts are primitive best effort. In between, you can able to preempt that to best effort. Okay, you can give the resources to advance reservation, and you can resume the work after AR is completed. Another thing you can notice here that the best effort lease has printed from node number 1, right? Which node that it is printed? The node number 1. So it has to resume in node number 1 only. It should not be given to any other node. So there is a justification for this one. For example, whatever files you have collected, right? If you are printing a particular lease, so temporary files are generated or partial result is with node 1. So whenever you are resuming that particular lease, so that partial result is with that particular node only. That is the reason once a best effort lease is permitted, it is going to be resumed in that particular node only. Okay. So here also you can clearly see AR lease is having more priority over the best effort lease. Okay. So there is another type of lease that is called as immediate lease. So I can say immediate lease is a lease where arrival time is same as start time. I told you in advance reservation lease, arrival time is less than the start time. For example, a lease has arrived at 12:30 p.m., but it is requesting to start at 2 p.m. Arrival time is less than start time. So you have some time, 12:30 to 2 p.m. to set up everything. But immediate lease is a type of lease where it will not ask you any time for taking any kind of setup. Suppose it is arrived at 2 p.m. So it will ask you to start at 2 p.m. only. Okay. So immediate lease is more priority. Right? If you look into everywhere, immediate is more sensitive. Right? It has to start, otherwise it has to reject. For example, at this point of time, it is making a particular request, but you are saying no, no, resource is not available. So what happens? This immediate lease is going to be preempted or it is rejected. Not preempted, it is rejected. Right? It will be rejected from the system. If resource becomes available, you have to provide. So immediate is more costly than advanced reservation because in advanced reservation case, you have some buffering time. But in this case, you don't have any buffering time. Once a lease is arrived to the system, immediately you have to start or you have to reject it. But it is always not fair. Like best effort case, you can delay the execution of a best effort lease for a indefinite period of time. That is the drawbacks. And in the case of immediate lease, you can take an instant decision, yes or no, whether to execute or not. So in order to avoid this one, both side, in the best effort lease side or you can say immediate side. So there is another lease which is developed that is called as B with the deadline lease, or sometimes it is called as deadline sensitive lease. So we will submit in best effort mode, but we will put a deadline. For example, now the time is let's say 3 p.m. Okay, you are making a request to a cloud service provider by saying that I need a 1 hour of resources. I need a 1 hour of resources, but this 1 hour I need before 12 midnight. So there is a deadline you are giving to your cloud service provider. So cloud service provider has to provide 1 hour before 12 midnight. It can provide 4 to 5. It can provide let's say 9:30 to 10:30, or it may provide 11 to 12. Anything is okay. But you should put a deadline. Within that deadline, if it is not serving, then the lease is going to be rejected. So earlier we say what? As soon as the resource become available. But now we are saying as long as my lease does not start or end any later than the deadline. So you can specify before 12 midnight it is going to complete, or before 12 midnight it has to start its execution. So if you add a deadline parameter with your deadline parameter with your best effort lease, then we call that as a B with the deadline lease, or we simply call this as a deadline sensitive, deadline sensitive, or DS lease. Okay, so DS lease is little bit stringent, so it is flexible, but the problem is that you have to fulfill that in a before a particular deadline. Okay, otherwise it is going to be rejected, or sometimes when you make a commitment, you have to pay the violation cost. If you have committed that before 12 midnight you will give 1 hour and you have not given, that means you are violating the policy. So you will be penalized. Right? That is the concept of B with deadline. There is another type of lease that is called as negotiated lease. Negotiated means just like a bargaining we are doing, right? So, for example, you requested, let's say, some resources to your cloud service provider, and you are ready to pay $100. Okay, if your service provider is going to provide you, then you are ready to pay $100, right? But your cloud service provider has seen at this particular period of time, it has to provide the resources, but due to some unforeseen or unavoidable circumstance, it is not going to provide you the resources. Maybe another lease arrived who offered uh, very high amount, right? So what your cloud service provider will tell you, you relax the deadline. For example, it is 2 p.m., right? It will say, I'll provide you resource at 4 p.m. instead of 2 p.m. Okay. So instead of paying $100, you pay $50. It is fine for me. Okay. Your provider is started bargaining, not a customer you are bargaining. Provider says that 2 p.m., which I have committed to provide the resources, but now I cannot provide due to some unavoidable circumstance. So you extend it to 4 p.m. I'll give you the resource at 4 p.m. And you can offer me $50, right? Similarly, let's say in 4 p.m. also the provider is not ready to pay it. Then provider will say, you change it to 6 p.m. and I'll provide you the service with $25. Okay. Or it will say it will, you extend the deadline to 12 midnight and I'm going to provide the service with $10. Or if you need one node, I can provide, let's say, 4 nodes. Okay, you extend your deadline up to 12 midnight. Instead of one node, I am going to pay 4 nodes. And you pay only $10. That is fine for me. So this type of lease is called as negotiated lease. Right? We are doing negotiation. Right? Over a period of time, it is doing negotiation. So generally cloud service providers are having enough resources, but there is a chance of this negotiation to take the advantages. Okay, let's say you have a 4 node cluster. Somebody offered you a very high amount and you are given 4 node cluster up to, let's say, 350. Okay, 350 up to this one. Then you can request your client to wait up to 4 p.m. and instead of $100, you can offer $50. Okay, like that, this negotiations happens between a provider and a consumer, right? So when you come to the actual cloud environment, for example, we have seen Amazon EC2 as a part of this course. In Amazon EC2, every allocation policy is considered as best effort. Whatever request you are making to Amazon EC2, it is treating every lease as a best effort lease. What is a best effort lease? Best effort lease means as soon as the resource become available, I am going to provide it. There is no question of ARBs. But when you go for Nimbus, Nimbus is another popular cloud platform. So that is treating all allocation policies immediately. You have submitted, that means it will immediately serve it. Similarly, Eucalyptus is also a popular toolkit in which uh, all the allocation policies are immediate. Open Nebula is also another popular platform, right? So in which allocation policy is best effort, like Amazon EC2. But when you go for Hygia Open Resource Manager, as a part of research, we are using Hygia. Right? It is easy to install. The manuals is also given to you. If you need it, I'll share this manual in our shared folder. So you can see the manual. And if you have a Ubuntu system, you can do it. Okay. So Hygia provides the allocation policy in AR mode, best effort mode, and immediate. So for example, you have set up n leases. Okay, n leases. Assume that n third number of leases are this advanced reservation. N third number of leases are best effort. N third number of leases are immediate. So if all these edges are given in some random order, how you are going to assign these n number of edges to a 4-node cluster? So in this case, I'm taking a 4-node cluster. I'm taking an example of 4-node cluster. How you will assign this n edges into 4-node cluster? So that is really challenging, and that problem is called as the resource allocation problem. Is it clear? After this, if you have any doubt, you can ask. Okay, so we'll see some of the examples so that you can understand actually how these resource allocation algorithms works. Okay, that is the first part of resource allocation. Now I told you in if you go to task scheduling, in task scheduling we have a directed acyclic graph. Okay, so here you can see an example of a directed acyclic graph. So in which we have 6 number of tasks. This is also a precedent constant application. Okay, each application is having a application ID. So here application ID is 1 and its arrival time is 0. Right? So we took a random application. Sometimes we took a random application, or you can go for standardized application. So there are various standardized applications are there that also you can use when you want to simulate your algorithm, right? So for example, if I ask you how you are going to assign these application into 2-processor system, or let's say first of all try with 1-processor system. 1-processor system means you can execute only one task at a time. So first you are going to assign A. Once A is completed, B, C, D, these 3 tasks can be executed in any order. So let me follow alphabetical order: B, C, and D. So once B is completed, you can start E. Once B and C is completed, you can start E. So B, C is completed here, so I can start E. Okay. Once C and D is completed, you can start F. So this is the sequence in which you are going to assign task to a single processor system. Obviously, single processor system is much more slower. So in order to avoid that, we can go for 2-processor system. In a 2-processor system, you have, let's say you have 2 processor here, right? So 2 tasks you can done simultaneously. So I can start task A, right? Once task A is completed, B, C, D can be executed. But I have only 2 processor. So if I have 2 processors, I can start B in one processor and C in another processor. But ensure that once you are completing A, the result of A should be sent to this particular processor. Okay, then only you can start C. So it also takes little bit of time. Okay, this time indicates transmission of the result A to C. Okay, that means communication from processor 1 to processor 2. Okay, so normally we consider this is negligible, but this time is always there. But why I am not considering any communication time here? Because both parent and child is assigned to same processor. So as A is executed in processor 1, its result is already there with processor 1. So if any of its child is assigned into that particular processor, then there is no communication time. Because the result is already with that processor, so processor need not communicate with another processor. That's why we consider that B is not going to take any communication time from A. Let's say B is completed here, C is completed here. As we don't know what is the duration of B and C, so I am taking it randomly. So now once B is completed, I can start D. So I will start D here. Again, for D also you will not get any communication time because D's parent is A. So that result is already with this particular processor. So there is no communication time. Let's say D is completed here. Now once C is completed, can we start E? Once C is completed, can we start E? You can see E. In case of E, both it is dependent on B and C. So B is completed here, C is completed here. So I can start E. Okay. and B and C. So C can start immediately E because C result will come to E, but B to E also it takes some time. So once B is completed here by this particular period of time, the result will is reach to processor number 2 because B has to also send the result to E, right? C has to send the result to E. Anyhow, this processor is same, right? Parent and child is assigned to the same processor. But what about B and E? So B has to send the result, so it will take also little bit time. So whenever we take a particular task having more than one parent, okay, if a task is having more than one parent, so if one of the parent processor you are executing that particular task, we are making that communication time is negligible. Okay, so now we have to start F. F is dependent on what? C and D. C is completed here, D is completed here. So I can start F here. Let's say F has finished here, E has finished here. So if you go for a two processor system, definitely it is taking less time in comparison to one processor system. Now, if you go for a three processor system, if you go for a three processor system, so now you have three different processors, right? So you can start A. Once A is completed, you can start B, you can start C, you can start D. So obviously there is a communication time. I am not worried about this time, right? Again, this time is also different with respect to one processor to another processor. Okay. And let's say B completed here, C completed here, D completed here. So now we have another two tasks, that is E is there. So where you can start E? You can start E after this particular period of time because B, C, it need to complete B as well as C. Until unless B and C is completed, you cannot start E. So if I want to execute here, then I will execute E here, but only after completion of C. Similarly, once C and D completed here, C completed earlier, but D completed here, then I can start F in processor number 2 or processor number 3. So again, if you see it is completed here, it is completed here, the time is required to complete in three processor system, it is less compared to two processor system and one processor system, right? But if I go for a four processor system, do you think the performance is going to improve? If I go for four processor system, let me add a processor here. I am assuming that this is fourth processor. Okay, so I am adding a fourth processor. Do you think the process execution time is going to be reduced? Yes or no? Obviously no, right? It is not possible, right? So for every application, there is a limitation. Once you go beyond that particular limit, the performance is not going to improve. So it is always challenging to choose appropriate number of processors, right, for a particular application. So I can give you a particular application and I ask you that determine the number of processors required to execute this particular application. As I said, these are a random application. This application is a complete random application, right? But there are many standardized applications are there which are used in various real life domains. For example, here you can see I am showing you three different applications. First application is montage. So montage application is used in the field of astronomy. So in astronomy, different components are organized like this, right? Whichever you can see in this particular data flow graph or directed acyclic graph. So they are organized like this. So you can see the complexity, right? So in the root part, there are four different nodes. Then we have six nodes followed by one node. Then four nodes, again one node, right? So I can ask you how efficiently you can execute this application. So in order to run this montage application, what is the minimum number of processors required that you have to determine? And how efficiently you are going to execute such that the overall execution time is minimum that you can ask. Similarly, there is another application that is called as epigenomics. So epigenomics is more or less a simpler application compared to montage. So epigenomics is used in the biology field. Okay. These are real life applications. These are not generated applications. So you can see In biology domain, again, these are different type of components. How they are connected, that is represented in the form of a directed acyclic graph, right? So you have to determine the number of processors, and you have to also conclude that how efficiently you are going to execute such that the overall completion time is minimized. For example, I can say in order to execute this particular task, it requires, let's say, 2 seconds. Then 1, 2, let's say 5 and 7. So this much time is required to propagate the result of this particular task into 4 different tasks, right? First task is taking 2 units of time. Okay, then it is sending the result to another 4 tasks. Let these are the tasks. Okay, but the communication between these two tasks takes one time. This is taking 2 units of time. This is taking 5 units of time, and this one is taking 7 units of time. Okay. Next, once these tasks are completed, again these tasks are having some time. Let it be 3, 7, 9, 8. Again, once it is completed, it is again connected to another 4 tasks. There also you have got some communication time here and some computation time here. So like that, you will see you have to determine the number of processors. Suppose you will decide that number of processors required is 4. Okay. And what is the overall completion time? If I am giving you for four number of processors, so what is the overall completion time to complete the epigenomics application, right? Similarly, there is another application which is also used in the biology domain, that is called as SIPST, which is little bit more complex in comparison to Montes and epigenomics. Now, see another 2 application. One application is called as LIGO, LIGO, which is used in the gravitational physics field. Another application is called as CyberSec. So these are the real life applications. So if you want to implement any resource allocation algorithm or task scheduling algorithm, okay, first you have to determine how many processors are required. That is called as a resource allocation. Once you decided that let's say 5 processors or 10 processors are required, then what you have to do? You have to determine that in these 5 processors or 4 processors, whatever given to you in resource allocation phase, how efficiently you will assign the task to different processors such that the overall completion time is minimized. Okay. So LIGO is used in the gravitational physics domain and CyberSec is used in the earthquake science domain. So out of these 5 applications, if you got, let's say, good result in more than 3 applications or 3 applications, then your result is going to be accepted. Because these are the real life applications, right? First, you have to implement in 5 different applications. Okay, not necessarily that 5 out of 5 applications you will get good result. They are having different structures. So in a particular structure, your algorithm may be better, right? Whereas other application case, maybe literature in literature, other type of algorithms are there. They are better. So in that way, one can distinguish one with others. Now, if you come to the task, as I told you, application, another is task. Task can be divided into two, but one is independent task, another is dependent task. Right? Independent task means you can say one task is can execute in any order compared to other tasks. Suppose I have n independent tasks, let's say 1, 2, 3, 4, 5. N is equal to, let's say, 5. So if n is equal to 5, let me T1, T2, T3, T4, T5. Okay, if they are independent tasks, they can be executed in any order. So I can start with T3, then T5, then T1, then T4, then T2. This order is also acceptable because they are independent, so nothing to worry. But dependent task means which we have seen in application. Okay, generally we represent dependent task in a directed acyclic graph, or we can take urgency matrix. Urgency matrix, we know it is a squared matrix in which we put a value 1 if there is an edge between two different tasks. For example, T1 is connected to T3, so it is 1. T1 is not connected to T2, then the value is 0. So we use urgency matrix to represent it. But independent task case, we represent in the form of a matrix. Okay, we represent in the form of a matrix. The matrix need not be a squared matrix. Okay, but dependent task, the matrix is a squared matrix. Again, if you go for independent task, you can execute the task in immediate mode or it can execute in batch mode. Immediate mode is called as online mode and batch mode is called as offline mode. Immediate means, for example, T1, T2, T3, T4, T5. There are 5 different tasks. If I execute them one after another, by keeping in mind when you are executing T1, T2, T3, T4, T5 is not there in the picture. Similarly, when you execute T2, T3, T4, T5 is not there in the picture. Or when you execute T3, T4, T5 is not there in the picture. So that is a sequence, or that is called as online mode because you don't have any idea. But in the base mode, what happens? A group of tasks is assigned to you. Let's say 5 different tasks is assigned to you. I'll ask you to execute it. So you have decided that this particular order may give a better value. So that type of mode is called as batch mode, or it is called as offline mode. So in the process of scheduling, what we are doing? We are simply making mapping between a group of tasks to the resources. One side we have a group of tasks, another side we have a group of resources, right? So we do a matchmaking process, right? First we are comparing a task with different resources, and let's say we found that this particular resource is more suitable for this particular task. Then we schedule a particular task to the resources. So always scheduling is performed through two phases. One is first phase, we are doing matching. We match a particular task with multiple resources or a subset of the resources. Then we schedule the task into an appropriate resources. So when you go for the independent task is instead of saying task, we call that is a meta task. So meta tasks are generally independent in nature. Okay. So main motivation of going for these two type of problem, resource allocation and task scheduling problem, is that mapping independent tasks onto a heterogeneous computing suite. That means suppose you want to map a task T1 into let's say 3 different machines, but these 3 machines are heterogeneous machines. Heterogeneous machine means when you execute T1 in machine number 1, it will let's say 5 minutes of time. But when you execute T1 in machine number 2, it is taking 7 minutes of time. When you execute T1 in M3, it is taking 10 minutes of time. Okay, so what do we have? We have heterogeneous time. Why we are getting different time? The reason is that these computer systems are having different architecture. They are having different capacities. They are obviously the time required to execute that is different. So mapping these independent tasks T1, T2 up to let's say Tn into heterogeneous computing suite where we have multiple machine is a well-known NP-complete problem. Okay, so if it is an NP-complete problem, if the throughput is the optimization criteria. The object is throughput, right? How much task you are going to execute, overall completion time of the all the task. So these are our target, right? That's why this is a very popular NP-complete problem. That's why many people have developed heuristic or meta heuristics to solve the task scheduling problem. Now you may say how to calculate how much time it will take a task in a particular machine, right? It is based on some parameter. So you can see in this slide. Assume that I have 2 resources. So there is 2 resource. Let us take this is your resource number 1, and this is another resource that is R2. Okay. So we have 4 different tasks: T1, T2, T3, T4. Okay. So you just want to know, want to find how much time it will take if I assign T1 to R1 or T1 to R2. So it depends upon 2 parameters from the task side, another 2 parameters in the resource side. For example, if you go for the task side, 2 parameter is volume of instruction, another is volume of data. For example, you want to process 200 million instruction, okay, and 20 MB of data. So every instruction is having data, right? If you take any instruction, if you take some load, load a particular register, move a particular register. So every register is having some data, right? Some content. If 8-bit register, 8-bit data you are going to change from one register to another register if you want to move it, right? So volume of instruction is 200 MI and task is 20 MB. So if you look into the resources perspective, resources also having two parameters. One is the speed. So speed of this particular resource is 100 MIPS. So it can execute 100 million instruction per second. Similarly, the bandwidth is 10 Mbps. Okay. So this computer speed is 100 MIPS, CPU speed, and related bandwidth is 10 Mbps. Similarly, R2 R2 is another resource. So it is having 200 MIPS. The speed is 200 MIPS and related bandwidth 5 Mbps. Okay. So you can see these two resources are heterogeneous resources because you can see their speed is different, right? Their bandwidth is also different. So in order to calculate how much time T1 is going to take in R1, so it is nothing but 200 divided by 200 is the amount of instruction you want to execute with 100 MIPS plus 20 is the bandwidth divided by 10 MIPS. So how much you will get here? You will get 4. Similarly, if you execute T1 in R2, it is 200 divided by 200 plus 20 divided by 5. So it is 5. So like that, this particular matrix is can be calculated. I will take T2. T2 is has to process 400 million instructions and 30 MB of data in R1 and R2. Right. So this matrix is called as expected time to compute matrix or expected completion time matrix also people say, or in short we call it ETC matrix or ECT matrix. So in this way you can calculate a particular task in different resources. However, if you look into this particular matrix, this matrix can be visualized in different way. So they are called as consistent, inconsistent and semi-consistent. Okay, matrix may be consistent or inconsistent or semi-consistent. So let us understand what is the difference. For example, you have a set of tasks, right? You have a set of resources. Okay, and you have calculated this ETC matrix. This matrix is called as ETC matrix. So now you tell me for task T1, which machine is better? So obviously the machine which takes less time, that is better. So R1 is better. For task 2, which machine is better? R1 is only better. For task M, which machine is better? Again, the first machine is only better. Right or no? So that is called as a consistent matrix. Consistent matrix case, if a particular resource is better for a particular task, so irrespective of the task, that machine is better. For example, if you see 25 is the second best machine, right? So R2 is the best machine for all other tasks. So that's why it is called as a consistent matrix. However, when you go for an inconsistent matrix, for example, if you take a ETC matrix like this, right? So for T1, R1 is better. For T2, Rn is better. For Tn, R2 is better. Right? So different machines are better in different type of application or different type of task. So you cannot find a particular pattern here. So that's why it is called as an inconsistent matrix. So inconsistent matrix case, it is difficult to determine which resource is better. Okay, whether T1 is better or T2 is better or Tn is better. Okay, that type of matrix is called as inconsistent matrix. Why these are the different type of matrix? The reason is that sometimes we can develop an algorithm which is better in the consistent case only. It is not better in inconsistent case. Sometimes we can develop an algorithm which is better in the inconsistent case but not in the consistent case. So not necessary that if a algorithm is better in the inconsistent, not inconsistent or vice versa, that is not a good algorithm. Right. So based on the type of logic you are using in a particular resource allocation or task splitting algorithm, that depends that whether your result is better in one case or not better in a particular case. So there is another type of matrix that is called a semi-consistent matrix. So semi-consistent matrix means, for example, here you can see the first best machine is R1 and T2 case first best machine is R1, but Tn case the first best machine is R2, right? So it is not called as a consistent matrix. Consistent matrix means I told you if R1 is better for T1, R1 is better for T2, then R1 is also better for Tn, right? But in this case, R2 is better for Tn. So it is not a consistent matrix. So obviously, if a matrix is not consistent, that is an inconsistent matrix, right? But semi-consistent matrix says that if you take a particular matrix and a part of the matrix, for example, you have taken a 5 cross 5 matrix and you found 3 cross 3 matrix is consistent, then we call that matrix as semi-consistent matrix. So it is a special case of inconsistent matrix in which part of the matrix is consistent. You can see these two tasks, you can find some similarity. Right? These two part is again R1 is the best and R2 is the second best. So they are called as semi-consistent matrix. Okay. Now coming to different type of algorithms, like we'll go for some of the resource allocation algorithms so that you can get an idea. So in resource allocation algorithm, they said lease is having certain properties. Like for example, in this case, you can see a lease is defined in the form of lease ID. ID is the unique identification number assigned to a particular lease, and a lease has arrival time, start time S, deadline D, period P, and number of nodes. So if you want to define a lease L1, for example, I'm saying lease L1, its arrival time is, let's say, 8:30. Okay, 8:30 it is arrived to the cloud service provider, but it is going to start at 9. Okay, its deadline is 10:30 and period is 40 minutes period and number of nodes required is 1. So if you want to define a particular list, you have to specify these parameters, right? So what is the problem here? The problem is that a set of resources and nodes are given to you, right? And a set of leases are given to you. Normally nodes means here we are taking a 4 node cluster or 5 node cluster. A set of leases are given to you, L2, L3 up to let's say Lm. Then your problem is to assign these leases to a 4 node cluster such that number of leases rejected is minimized. Or you can say number of leases that is accepted is maximized. Okay. So take an example. For example, if you look into this example, here we have how many leases? We have 7 different leases. L1, L2, L3 up to L7. Their arrival time is given, start time is given, deadline is given, and duration is given, this period is given, and number of nodes is given. Okay, and all these leases are sorted based on their start time. Okay, in fact, they have also sorted it based on the arrival time. But start time has more significance, right? Because at that time you have to start allocating the resources. Okay, normally it is arranged based on the arrival time, right? But in order to process, you need the start time. So we go for the algorithm which is given in Hygia, right? If you install Hygia and submit a set of leases, so generally these leases are XML documents. If you go for the lease file, I'll show you the lease file. In the lease file, you will see the leases are written in the form of an XML document, right? Every lease is represented in the form of a XML document. So what you need? You need an XML parser. What XML parser is going to do? It has to read the document and can summarize whatever requirement or whatever things you require that can be retrieved from this XML document through an XML parser, right? So for example, if you go for Hygia, if you are giving set of leases, what it will do? For each lease, it is going to find a single time slot. For every lease, it is going to find a single time slot. But sometimes while you are assigning to resources, you will find that single time slot is not available. So if single time slot is not available, it will call the process of rescheduling. Okay, rescheduling means suppose you have assigned L1, L2, L3, and while L4 is coming into the picture, okay, when L4 is coming into the picture, you are not getting a single time slot. What you will do? You will call rescheduling. Rescheduling of which leases? L3, L2, L1. For example, after reordering it, let's say L3, L1 followed by L2, you can accommodate L4. Then this rescheduling is accepted. But after doing this one, let's say it is not possible to L4 to accommodate in the system, then you are going to roll back to your previous order. So while you are performing the rescheduling, what we are doing here, we sort the leases based on the slack value. So there is a formula for slack value. We calculate the slack value and order these leases based on the slack value. Okay. So many authors also suggested that why there is a single time slot, why not there is a several time slot. For example, why it is 9 a.m. to 10 a.m. rather than taking 9:30 or 9 a.m. to 9:30 a.m. Okay, then you can take another slot from 10 a.m. to 10:30 a.m. That also fulfills your 1 hour, right? So instead of taking a single time slot, they suggested to go for several time slot. So let us see one example to clear our idea. Now here in this slide, you can see there are 5 different leases, right? Their arrival time, start time, deadline, period, and number of nodes are given, right? So now coming to L1, what L1 is asking? L1 is asking within the time 12 to 13:20. Okay, 12 to 13:20, it is asking for a 40 node slot, and number of nodes required is 2. What I did, I have assigned node number 3 and node number 4. It has to start at 12. So it requires 40 minutes. 40 minutes means it will complete at 12:40. Okay, before 13:20 you have to complete. Okay, before 13:20 you have to complete, but all the nodes are free. So I have assigned node number 3 and node number 4 to list number 1. So you can assign the node number 1 and node number 2 also. There is no issue. You can assign 1, 3 also. You can assign 2, 4 also. Any two nodes you can assign. For easy representation, we are filling bottom to up. Okay. So L1 is now satisfied. Now coming to L2. L2 is asking 12 to 13:20. It is asking 3 node for 20 duration, 20 minutes duration. So if I start at 12:40 with 3 nodes, because before 12:40 it is not possible to give 3 nodes, because total you have 4 nodes. You have assigned 2 nodes to L1. So it is not possible for you to assign, it is not possible for you to assign 3 nodes to L2. So L2 can get service from 12:40 onwards only. So 12:40 plus 3 nodes, right? So 3 nodes for 20 duration. So if it starts at 12:40, 20 means it will go up to 13. 13 means 1 p.m. It can satisfy the requirement. So L2 is satisfied. Now coming to L3, it is also asking from 12 to 13:20, but it is asking 4 node for 20 duration. So if you start at 13, it will complete by 13:20, right? And we can provide 4 nodes, right? That is available. So L3 requirement is also satisfied. But what about L4? When L4 is coming to picture, L4 is asking 12:30 to 13:20. 12:30 is this one, 13:20 is this one. So in these slots, it wants 40 minutes. 40-minute period for one node. So one node slot is available here. So this slot I can provide, right? But what is the duration? 12:30 to 1. That means it is a 30-minute slot. Okay, it is a 30-minute slot. But what we need? We need a 40-minute slot. Although 10 minutes is available here, but I cannot overlap with these two. I cannot overlap these two. and after this period of time, L4, L3 is already occupied. So it is not possible for you to assign L4 to the system. Okay. So what this algorithm suggests? This algorithm says that find a single time slot. So I have found a single slot for L4, but there is no single time slot. So if there is no single time slot, what you can do? You can go for the process of rescheduling. Okay. Rescheduling means whatever leases assigned before that, you have to perform rescheduling. So what are the leases that are assigned in between that particular period? That is 12:30 to 13:20. This is 12:30 to 13:20. You can see L1, L2, and L3. These are the three leases that are scheduled. Okay. Because when a new lease is arrived, if 100 leases are arrived prior to that, we cannot make rescheduling of 100 leases, right? But we can make a uh, rescheduling of the leases which is overlapping with this 12:30 and 13:20, because its duration is 12:30 and 13:20. Anything is assigned before this or after this, we need not bother, right? So L1, L2, L3 is coming. How to perform rescheduling? In order to perform rescheduling, you have to sort the leases based on the slack value. So what is a slack value? So for example, slack value is calculated as deadline minus start time divided by period. What is the deadline for L1? Deadline is 13:20. What is the start time? Start time is 12. Period is 14. So 13:20 to 12 means what is the duration? It is 1 hour 20 minutes. 1 hour is 60 and this is 20. So it is 80. 80 divided by 40 is 2. Similarly, you can calculate what is the slack value of L2. That is 1320 minus 1320 minus 12 divided by 20. So it is 80 by 20. So you will get 4. Okay, once you determine the slack value, you have to order them based on its non-decreasing order of slack value. Sort means it is non-decreasing order of slack value. So it is coming as 2, 4, and 4. Okay, 2 and 4 and 4. So there is no change in the order. Okay, 2, 4, 4 is already in the sorted order. There is no need to change. Okay, so L4 is not possible to assign as per this particular algorithm. So what we have to do? We have to reject the lease number 4. Now coming to L5. L5 is asking from 1240, this is your 1240. 1240 to 1320, it is asking 2 nodes. So obviously within this duration, 2 nodes is not available. Okay, 2 nodes is not available. If you do also rescheduling, it is practically not possible because it is already in the uh, increasing order of stack value. So what is the conclusion? L5 is also going to be rejected. So using Hygia, we can accommodate 3 out of 5 leases. Okay. So although I have suggested you here that enhancement is that you can go for several time slot. So practically several time slot. Also, if you implement in this idea case, there is no improvement. So you will have able to accommodate how many leases? You will have able to accommodate only uh, 3 out of 5 leases. Okay, is it clear or any question? Yeah, anybody is having any question? Okay, if there is no question, I'll proceed. So here I am showing you another example. So you can try this example in later point of time. Due to lack of time, I am skipping this one. Okay. Here also you can see L1, L2, L3 is assigned. L4 we are not able to assign because the slack values are already in the sorted order. However, after rejecting lease number 4, after rejecting this particular lease number 4, you can accommodate L5, L6, L7. So whole total you are accommodating 6 out of 7 leases using hygiene. Okay, you can implement this algorithm in any programming language, but in order to fill the cloud computing environment, you have to implement in hygiene. Otherwise, you can simply create array. Okay, you can create array in any programming language, and finally you can assign and see that how many leases your is going to be accepted. So in order to avoid the drawbacks of the DPS, the drawbacks of the hygiene algorithm, there is another algorithm that is called as DPS algorithm. So DPS algorithm uses these steps. What it does first, it is calculating the slack value first. Earlier, you are calculating the slack value if a lease is not assigned. Slack value is not calculated in Hygia if all the leases are uh, successfully assigned, right? If a lease is not assigned, then only we are going to calculate the slack value. Rescheduling case, we are calculating the slack value in order to sort them in a particular order. But DPS says that first you calculate the slack value. And if you found the slack value is less than 1.1, then you simply reject that particular lease. For example, let's say lease L1, its start time, is, let's say, 9. Okay, and its start time is 9, and let's say its duration is 60 minutes, right? Duration is 60 minutes, or you can say deadline. Let me write it, D is deadline. Deadline is 10, okay, and period is 60. So if you calculate slack value, what you will get? Slack value formula is deadline minus start time divided by period. So deadline is 10, start time is 9, divided by period. Period is 60. So 60 divided by 60, it is equal to 1. So slack value is 1, right? 1 less than equal to 1.1. That is true. So that particular lease is going to be rejected. So you see, it is giving you a 60-minute duration and is asking for 60-minute duration. So it is a rigid lease. That's why we are rejecting it. If it is greater than 1.1, okay, if it is giving sufficient time, then first you go for the single time slot like previous one. If single time slot it is not possible, if you are not able to accommodate, go for multiple time slot. If you got the solution, job is done. But if still you are not getting any slot after single time slot or multiple time slot, then you have to go for the process of rescheduling. So in the case of Hygia, when you do the rescheduling is based on the slack value. But in the case of DPS algorithm, the sorted is based upon the decreasing order of the node. It is based on the number of nodes, right? And if rescheduling also unable to fulfill your demand, then you have to apply the process of backfilling. And rescheduling and backfilling, if both are failed, then you have to reject that particular lease. So in this way, the DPS algorithm works in cloud environment. So let us take an example to understand it. So now I am taking the same example so that you can understand. L1, L2, L3 are the three different leases. Okay, their slack value also calculated. All the slack values are greater than 1.1, so nothing to worry, right? So they are allowed to execute. So I have assigned L1 first, then L2 second, then L3 third. So you will get a sequence like this, which we have seen here. L1 followed by L2, L3. Whatever you got in Hygia, the same thing you will get in the case of DPS algorithm, right? But now L4 is coming. L4 is not getting any space because L1, L2, L3 occupied the space. So we are not finding a single time slot for L4. We are not finding a multiple time slot for L4 also. So you can see in the algorithm, single time slot we are not getting, multiple time slot we are not getting. What is our next step? Our next step is to go for rescheduling. If you go for rescheduling, what you have to do? You have to sort the leases in the decreasing order of n. So what is the number of nodes here? Number of nodes is 2, 3, 4. If you go for decreasing order, then L3 will come first, then L2, then L1. L3, L2, then L1. So let us go to that slide. So you are assigning L3, L2, L1. So you can do rescheduling. One particular condition is there. The condition is that if you reschedule, earlier it is L1, L2, L3. Now we have changed to L3, L2, L1 based on the decreasing order of, this is the decreasing order of the number of nodes, right? N mode. So you can do it. So if there is no violation, so if you order L3, L2, L1, still they are satisfying their request. L1, L2, L3 order, their deadline is not violated, and L3, L2, L1 case also the deadline is not violated, right? So it is allowed. Okay, you can keep this sequence, right? Now you check for L4. L4 is asking 12:30. 12:30 is here. 12:30 to 13:20, right? So it is asking you 40-minute slot for one node. So 40-minute slot is available. So I am able to assign L4, right? In case of L5, now L4 is satisfied. L5 case, L5 is asking two different node. Okay, two node for 10 unit. 10 is the duration between 12:40, 12:40 to 13:20. Yes, there is a two node slot is available here. So L5 is also accepted. So where IGI accepted how many leases? IGI accepted 3 by 5, whereas DPS algorithm accepted 5 by 5. The number of leases accepted is more in the case of DPS. Alternatively, what we can say? We can say the number of leases rejected in the DPS case it is minimum. So DPS provides better result than what? Our DPS provides better result in comparison with the IGI. Then there is another algorithm that is called as alert time based resource allocation, that is called as ALTRA. So here what we are doing, first you have to sort the leases based on the start time. Okay, if it is not, normally it is in the order of start time. If it is not there, then you have to sort them in the based on start time. Then if one or more leads is having the same start time, you should put them into one group. Okay, if multiple leads are having same start time, you have to put in the same group. For example, you can see these are the leases that are having same start time, so they are put in the same group. These are the two leases that are having same start time, they are put in another group. This is the lease, only one lease that is having different start time, so they are put in another group. So I created three different groups. Then it is asking you to calculate the alert time. So how to calculate alert time? Alert time is nothing but D minus P. So for example, for lease L1, its deadline is 10:30, right? Its duration is 40 minutes. So 9:50 is the alert time. What do you mean by alert time? Alert time means if you are not starting a lease at 9:50, then the lease is going to be rejected. Obviously, if you somebody is asking 40-minute slot and deadline is 10:30, so if you start at 9:50, then only you will be able to complete it before that time. Otherwise, it is not practically possible, right? So we have determined the alert time. Then assign earliest alert time first. So if you see in the first group, these are the alert times. So after calculating alert time, you found L1 is having alert time, L4 is having earliest alert time. That is 9:50. So first you need to assign L1, then L4, then L2, then L3. So in this order, you are going to assign. So if there is any tie, for example, in this case there is a tie, right? So L1, L4 case there is a tie because both are having alert time 9:50 and 9:50, right? If there is a tie, so what you have to do? You have to look into the number of nodes. Okay, you have to look into the number of nodes, that is 1 and 4. Obviously, L4 is having more nodes, so the sequence you will get L4, L1, L2, L3. So in this order, you have to assign it. Okay. So if there is a tie, the tie can be breaked with the maximum number of nodes. So if there is no, if there is after that also it is not possible, then you have to apply the process of swapping. Okay, you assign the leases. If there is any conflict, so you have to apply the process of swapping. So scheduling is called as the process of swapping. Okay, previous case I am saying rescheduling. Here I am saying it is the process of swapping. So in swapping, what you will do? You will form, there are three different lease sets. For example, a lease is arrived at 8. Okay, its earliest time is 9:50. Okay, deadline is 10:30. So this is my start time, this is my alert time, and this is my deadline. So that is what you are finding. You are finding, you are making a set between start time and alert time. This one. Another is alert time and deadline. Another is start time to deadline. So you are forming three different states. ST to LT, ALT to D, and ST to D. Then you are finding ST to ALT. Whatever leases are coming under ST to ALT, you are finding intersection with ALTD. For example, L1, L2, L3 is coming under this one. Again, L1, L2, L3 is coming here. So in the previous algorithm like DPS and Hygia, while you are comparing this same set with another same set. So you are doing unnecessary comparison. In order to avoid that, it is finding STLT intersection LTD. Okay. And if none of the lease deadline is violated, then you apply the process of swapping. Okay. But if the swapping is also not successful, then you have to go for the process of backfilling. Again, if swapping is not successful, backfilling is not successful, then finally you have to reject the leads, right? So this is the way the ALT-array actually works. So you can see if you assign an ALT-array, first, as I said, L4 is going to assign, then L1, then it will go to L3, sorry, L2, then L3, okay, then L5, L6, L7. Okay, L5, L6. So no, L5, L6 case, you will go for L6, then L5. So the order is L4, L1, L2, L3, then L6, L5, and L7. So in this order, you are going to assign it. So you can see 7 out of 7 leases are accepted in ALT array algorithm. Okay, so there are some performance matrices that you have to use to compare the resource allocation algorithm. You have to consider number of accepted leases, number of rejected leases, number of leases insisting rescheduling. For example, L1, L2, L3 are the three leases, right? L4 is a lease which is insisting L1, L2, L3 to be rescheduled. So that will be counted as one lease here. How many leases are insisting other leases to rescheduling? That count you have to do. And if it is insisting, if these leases are rescheduled into L3, L1, L2 order or some other order, that will come under the number of rescheduled leases. Okay, leases insisting rescheduling and number of leases rescheduled leases, right? And there is a well-defined data sets for this comparison. So the data set is having 11 number of leases, 22 number of leases, 33 and 44 number of leases that is available in public domain. So you can try and compare whether your approach is better than IGA, DPS and AFTRA algorithm. If it is there, then that is obviously a better way. Next, there is another popular resource allocation algorithm that is called as fairness-based algorithm. So we have seen different type of leases. We have seen advanced reservation lease, best effort lease, immediate lease, and we have also seen negotiated lease, best effort with the deadline also we have seen, best effort also we have seen in permittable mode and non-permittable mode. So always, if you look into the AR lease and B lease, AR lease is having specific start time and end time. B lease is having duration, but there is no specific start time and end time. So if always AR lease is arrived to the system, so B lease will never get a chance. So it is not a paired one. So the solution is to go for a non-primitive based effort. So once a based effort is started, so it has to continue its work until unless it has done its completion. But still, in non-primitive based effort, if somebody will not get a chance, so it will not able to continue, right? Or as an alternate solution, you can say few based effort leases need to be scheduled before the advanced reservation lease. For example, here you can say at t is equal to 0, a best effort lease is arrived to the system and it is asking the duration of 5. And let's say your system is completely free. So you have started that particular lease for 2 unit of time, right? At t is equal to 2, time duration 2, a AR lease arrived to the system which is asking 5 duration from 2. So this best effort lease is printed. It is asking 5. So it is scheduled up to 5. Okay. But as AR has more priority, this is a primitive based effort. So what happened? The best effort lease is printed and AR lease is started its execution. Okay. So AR lease has started at 2. It has continued up to 5 unit of time. It has completed at 7. And once it is completed its execution at 7 unit of time, again the 3 unit which is left for this best effort task, just 2 unit completed here, so another 3 unit of task it has to execute after execution of A. But if you see at 7 unit of time, if another set of AR leases arrived, okay, suppose at 8 unit of time, not at 7 unit of time, 8 unit of time, again set of AR leases are arrived. So it is executed 2 unit here and 1 unit here. Then we are giving chance to this advanced reservation leave. So it will start at 8 and continue up to 13. Then another 2 unit it can execute and it will complete its execution at 15 unit of time. Okay. So other B leases are arrived in between which request 3 unit of time and 1 unit of time. So due to arrival of other AR leases like 15 to 318, 18 to 220 and 20 to 323. So these A B leases are put on hold. So there is always a challenge and how to provide fairness among the advanced reservation leads and best effort leads, right? If you can develop an algorithm where you can show that the best effort approach is better, some best effort leads are at least given priority over the advanced reservation leads, obviously that is going to be accepted. Okay, any doubt up to this? Yeah, very good question by Rita madam. That is what is backfilling. So I missed that one point. So I told you there is a process of backfilling here. So backfilling is like whenever the scheduling process, rescheduling page is failed, then we go for the process of backfilling, right? Let us see what is actually backfilling. So normally, if you take a railway reservation counter into consideration, suppose you want to book a Tatkal ticket, right? You know Tatkal time is let's say 10 a.m. right? 10 a.m. you can book the Tatkal ticket. So you arrived the railway station at say morning 5 a.m. and you are first in the queue, right? But your request is going to be served at 10 a.m. only. Let's say reservation counter starts at 8 a.m. right? So those people who are in the queue next to you, all are not waiting for your Tatkal ticket. They are waiting for normal ticket also. So their request can be solved between 8 a.m. to 10 a.m. Right? For example, you are waiting for Tatkal, this person is waiting for Tatkal, this person is waiting for Tatkal. But these persons are not waiting for Tatkal. They are waiting for normal tickets. So what we can do between 8 a.m. to 10 a.m. they can get service. Okay. And once it is exactly at 10 a.m., then you will get a service. What we are doing, we cannot hold. You are going to book a Tatkal ticket, so we cannot hold it for up to 10 a.m. right? Because your request is going to be served only at 10 a.m. but other requests can be served before that one. So the approach which we are doing here, that is called as backfilling. So if other user can satisfy their request before your time, then we are giving chance to them. That is called as the process of backfilling. Have you understood what is backfilling? Yeah, thank you. Okay, so I'll go for the last resource allocation algorithm, that is called as posted price model. I told you posted price model is based upon a mathematic popular algorithm that is called as Hungarian algorithm. Okay, what Hungarian algorithm says, generally posted price model applicable when number of tasks is same as number of resources or number of clouds or number of machines. But in real life, the number of tasks are quite more in comparison to the number of clouds. So what process you have to do in posted price model? If you are given with a resource allocation matrix like this, okay, assume that these are the times or cost or whatever may be, right? So first, if you apply Hungarian algorithm says that first you have to find the row minimum. What is the row minimum in this T1? The row minimum is 0.23, right? So once you find the row minimum, you subtract the row minimum from each and every element on that particular row. So if you subtract it, you will get C4 value is 0, right? Let us take T6. Which one is minimum? The minimum is 0.31. If you subtract it, this value becomes 0. So row minimum is 0, right? Now coming to, once you have done row minimum, then you find the column minimum. For example, in this case, if I find the column minimum, you will get 0.11 is the column minimum. So that you have to subtract from all the values. Okay. So this becomes 0. This one also becomes 0. You can notice here. So we are finding column minimum. Once you find the row minimum and column minimum, what you have to do, you have to see what is the minimum number of lines required to cover all zeros. You can see there are so many zeros in this matrix, right? Okay, just like a sparse matrix is having so many zeros. So you have to cover these zeros with minimum number of lines, not maximum number of lines, minimum number of lines. Maximum number of lines is always 6. 1, 2, 3, 4, 5, 6. So I have covered all elements with 6 lines. That is the maximum number of lines. But I am asking you to go for minimum number of lines. So the minimum number of lines you are getting to cover the zero element is 4. So it is expected to 6, but it is getting, you are getting 4. So if minimum number of lines is not same as the number of rows, like here number of rows is 6, or number of lines, minimum number of lines required is 4. So what you have to do? There is a mismatch. So if there is a mismatch, add the minimum uncovered element to every covered element. Which one is uncovered element? Those elements are not striked out. They are called as uncovered element. Which one is minimum uncovered element? Minimum uncovered element is 0.08. You can find in many places. Okay, many places. So that is the minimum uncovered element. Minimum uncovered element is 0.08. That you have to add to every covered element. Covered element means those elements are striked out. And if a element is striked out twice, like this 0.18, you have to add twice. So you will get a matrix like this, 0.18 plus 0.08 plus 0.08. Okay. So once you add the minimum uncovered element to every covered element, again what you have to do, you have to find the minimum element in whole matrix. The minimum element in the whole matrix you will find 0.08 in multiple location. So that 0.08 you have to again subtract from all the elements. So if you subtract 0.08 from all the elements, you will get a matrix like this. Again, what you have to do, you have to cover the zero elements with minimum number of lines. So minimum number of lines required to cover this element is again 6. Okay, in previous case it is 4. In this case it is 6. So it is same as the number of rows. So we'll stop here and assign the task to the corresponding machines. For example, here you can see T1 can be assigned to C2, it can be assigned to C4, it can be assigned to C5 and C6. However, if you look into T3, it can be assigned to C1, it can be assigned to C3, C5 and C6. Like that you find the possibility, the task with less possibility. For example, if there is a task is having only one possibility. Like you can see T2 case, there is only possibility C4. So you have to assign T2 to C4. And once a task is assigned to a particular machine or cloud, other task cannot be assigned to that particular machine. So if you look into this particular matrix, this one, whatever you are looking into these ones, okay. So these are the assignment of tasks to the different machines. So you can see per machine, we are getting exactly one task from posted price model. So this is another resource allocation model. Like that, there are several resource allocation model available in cloud, and it is also extended to the fog computing. Yeah, any doubt in this posted price model? Okay, so if there is no doubt, then I'll tell you the task scheduling very quickly because we have less time. So in task scheduling, what we are doing? So in the task scheduling, I already said to you, you have to find the ordering, right? So you can follow a centralized approach or you can follow a distributed approach. For example, if you see here, a user is making request to a centralized portal, right? That centralized portal is having information of all the clouds, and every cloud is managed by a manager server. This is a manager server which keeps tracks of the resources of its cloud, and all the information is with the centralized manager. So whenever a request is reached to the centralized manager has to consult with the manager server of various clouds to take a decision that who is going to execute the task of this particular user. Right? That is called as a centralized step. But the problem with centralized approach is that if centralized node is failed, then it is difficult to keep track of all the manager server and their corresponding cloud. That's why centralized approach is not a good solution because it is prone to single point of failure. So in order to avoid this one, what happens? A user may request to a manager server with its application, and you know application is represented in the form of a data flow graph or a directed acyclic graph. Okay. So once a manager server receives a particular application, it has to see its availability of the resources. Based on that, it can keep some of the requests, and some of the requests it can redirect to other manager server in consultation with that manager server. For example, it is saying A and D I am going to execute, so it will be put in my own queue, and E I am sending to another cloud, so that cloud is going to execute E, right? So in this way, that application is created by a particular manager server and sent to different clouds to execute. Again, this manager server has to consolidate the result and return the result to the corresponding user, right? However, this particular application, whatever you are observing, it may be advanced reservation application or it may be a best effort applications, which we have discussed earlier, right? And every manager server is having information about its cloud. But all the clouds which are participating in the network, they are having different capacity. As they are having different capacity, okay, in different clouds are having different capacity. So as they are different capacity, we call that is a heterogeneous cloud. So in this environment is called as heterogeneous multi-cloud environment. Okay. For example, you can see here, I have three different applications, right? Application 1, application 2, and application 3. They have different arrival time. Arrival time 0, arrival time 3, arrival time 9. So if I provide the properties of these particular application or task and properties of the clouds or resources, then you can calculate ETC matrix. I told you how to calculate ETC matrix. So it is based on volume of instruction, volume of data, processing speed, and bandwidth. So once you calculate this particular matrix, you can observe that this matrix is an inconsistent matrix. It is not a consistent matrix. It is a inconsistent matrix. So if you apply task scheduling algorithm here, for example, if you go for round robin algorithm, so round robin algorithm says that first task is assigned to the first cloud, second is assigned to second cloud, third is assigned to third cloud, fourth is assigned to the first cloud, fifth is assigned to the second cloud. Again, here 1, 2, 3, 1, here 1, 2, 3. So this sequence you will get in the round robin. So based on the arrival of this task, that is going to be assigned to different resources based on the round robin algorithm. But obviously, it is not a fair algorithm because we are not looking into how much time it is going to take in different machine, right? We are not looking how much time it is going to execute in this machine. So obviously, round robin will perform poorly in this case. So in order to avoid that, we are going for another algorithm that is called as least scheduling. Least scheduling says that out of these three cloud, which one is best? Obviously, if a cloud is taking 2 unit of time, that is best. In this case, if it is taking 4 unit of time, that is best. In this case, it is taking 3, that is best. In this case, this 5 is best. So that cloud it is going to assign. Okay, least scheduling always assign the task to a cloud which takes a minimum time. Okay, so in this way, various task scheduling algorithms are developed. However, many researchers also suggested in high performance cluster computing or grid that how to process a single application. For example, here, if you look in the previous case, here I am showing you only the computation time, but I am not showing you the communication time. Like I am not showing what is the communication time between A to B, A to C, B to D, B to E, C to E, that I am not showing. So in order to go in a deeper view, in this slide, I have shown the computation time as well as the communication time. For example, this one is treated as our computation time. So executing the task T1 requires 5 minutes of execution computation time. But this 4 and 7 is the communication time, right? So how to process this particular task into different machines? That is challenging. So there is a measure called T level. T level says that you find the path from entry task to the given task. For example, let's say entry task for all the task is T1. Suppose I want to find the T level of T3. So T level of T3 you can calculate in two ways. You can calculate via T2 or you can directly. So if you go for entry task to the given task, so it will come, if you go through this particular path, it will come 5 plus 4 plus 7 plus 12. 5 plus 4 plus 7 plus 12. And you will not consider the computation time of the given task. Similarly, if you follow this path, direct path, you will get 5 plus 3. So you will get how much? 9 plus 7 is 16 plus 12, that is 28, and this one is 8. Right? So if there is multiple path, you have to choose the maximum one. So T level of T3 is calculated as 28. Okay. So once you calculate T level of all the task with the least T level, which task is having with least T level? T1. So it has to assign first. After T1, you have to assign T2, then T4, then T3, sorry, then T5, then T3, then T6. In this order, you are going to execute it. So this ordering is determined based on the T level. So there is another level that is called as a B level. So now we are calculating from entry task to a given task. In this case, you are calculating given task to the exit task. For example, if you go for T5, T5 is a given task, exit task is T6. So there is only one path. So it is 2, this 2 plus 5 plus 8. So how much you will get? It is 15. So B level of T5 is 15. Similarly, you can calculate B level of the other task and assign the task with maximum B level. So who is having maximum B level? T1 is having maximum B level. So T1 is assigned first, followed by T2, followed by T4, then T3 and T5 in any order, then followed by T6. Similarly, there is another parameter that is called as a static bottom level. Static bottom level is same as our static bottom level is same as our B level. B level case also we are calculating given task to the exit task. Here also we are calculating given task to the exit task. But the thing is that here only you are considering the computation time. You are not going to consider the communication time. Okay. So for example, if you go with this one, for example, if I calculate for T5, so T5 is the given task, T6 is my exit task, right? So computation time only I'll calculate 2 plus 8, that is 10. For example, if you take T4, T4 can be reached like this, or like can be connected like this. So it is 4 plus 8, so you will get 12. If you go through T5, it is 4 plus 2 plus 8, so you will get 14. And if multiple paths are there, you will choose the maximum one. So static bottom level can be calculated like this, and based on the maximum static bottom level, you have to assign the task. That means T1 is to assign first, followed by T2, then T4, then T3, then T5, then T6. So in this order, static bottom level assign different tasks to the resources. Okay, the last one which we can see, that is called as ALAP. ALAP stands for as late as possible. In order to calculate as late as possible, first you have to determine the critical path. Okay, then you have to find the path between exit task and given task. So critical path means starting from your entry task to the exit task, starting from the entry to the exit task, you go for all possible paths and find the longest path. The longest path you will get is 43. Okay, so if you want to find ALAP of T6, so 43 minus 8, so you will get 35. So you can see here 35. Okay, that is critical path is your 43. Okay, then path from exit task to the given task. Let's say exit task is in this case which one? T6. Given task is also T6. So you will get 35. Right? But in this case, if there are multiple paths are there, like here you can see multiple paths, you will choose the minimum one. Okay, you will choose the minimum one. And you will choose the task with the least ALAP is assigned first. Okay. So what we have discussed in this 2-hour session, we have seen there are 3 different algorithms. One is Hygia, another is DPS, another is ALTRA. Okay, these are the 3 connected resource allocation algorithm. Then also I have seen fairness algorithm and posted price model. And in task scheduling, we have seen round robin scheduling algorithm and least scheduling algorithm by considering multiple workflow or multiple application. And we have seen some of the measures like T level, B level, S level, and ALAP to determine the order of the task to execute in different applications. So you can refer, these are the some of the papers that can be that you can see, which is related to this particular resource allocation and task scheduling problem. Yeah, thank you everyone. If you have any questions, you can ask.